Today's lecture, the continuation of the previous two classes. In the last two classes, we gave an introduction related to Lebesgue integral and some of the shortcomings of Riemann integral and pictorial representation with an example. Lebesgue, these things we discussed in the last two classes. Is it correct? In this class, we plan to discuss on Lebesgue integral with respect to some of the Riemann integral format. Then we will move on to the Lebesgue integral of a bounded function over a set of finite measure, and also some of the important theorems related to simple function with a finite measures we will discuss now. Some of you are not aware of that. These are the things we discussed in the last class. This is the representation, and also we gave a short movie related to this Riemann and Lebesgue integral things and intuitive representation we discussed in the last class. Maybe some of you are checked this Lebesgue and Riemann integration, how it is excellent version related to integration, related to volume and area related concepts. The Lebesgue integral, first we will start with the Riemann integration. We can recall. First, let f is a mapping from closed interval a comma b to r be a real valued function. And let a is a, here a and b can be subdivided into intervals, that is xi0 less than xi1 less than xn minus 1 less than xn. The starting point is a is equal to xi0 and xn is equal to b. We can make a partition and make it into a, this AB can be divided into equal parts, be a subdivision of closed interval a comma b. And let us make a function mi is a supremum of f of x, and it is lies in the delta I, means that is x lying between each the partition that is in the equal length, that is I running from 1 to etc. n. And you already seen in this pictorial representation in the last class. Similar way, here small mi is the infimum of f of x into delta xi. Means delta xi means it is lies between, x lies between xi minus 1 to xi. And the another representation we are use, that is s is equal to capital S is equal to summation I running from 1 to n into mi. Some of the textbook they are written as delta xi. That is same as xi minus xi minus 1. Similarly, small s is the representation of summation I running from 1 to n xi minus 1 into small mi. You know that mi, small mi is the infimum of f of x and capital Mi is the supremum of f of x. Then we can define the upper Riemann integral and lower Riemann integral in this way. The upper Riemann integral R of integral upon a to b bar f of x is defined by R, and also R of a lower limit integral upon a to b f of x dx is equal to infimum of s, infimum of this capital S. Here this is upper Riemann integral, R of infimum of s, this is equal to infimum of s, and the lower Riemann integral is equal to as R into integral upon a, here lower b f of x dx is equal to supremum of small s. These are the things you already aware. If you take the infimum and supremum, because depending on here infimum is there, you can take a supremum. Here supremum is there, here you can take a supremum over all the subdivisions of closed interval a comma b. Then this f should be a Riemann integral if r of integral upon upper Riemann integral is equal to lower Riemann integral, that is equal to the Riemann integral, or it is denoted in the common value. If these two are equal, then we define in this way. Lower and upper Riemann integrals are same, then we write r into integral upon a to b f of x dx is denoted by the common value. Here there is a small example related to it is an integrable, but we cannot integrate in a Riemann integrable. Consider the function f of x. If x is a rational, then we can represent 1. If x is irrational, we can make it as 0. These things you know that here. Here, if you make x is a rational number, we can represent that is here 0, 1, 2, 3, somewhere. Sometimes we make a represent as 1 and 2 and this one. Otherwise, it becomes 0. Is it correct? Here, if f is not Riemann integrable on closed interval a comma b, then since you know that the definition of Riemann integral, upper Riemann integral is equal to, what is that? Infimum of all the sum. Here, Riemann integral is infimum of small s. Here, infimum of small s means here you get 1. Infimum of all the function means you get that is infimum of s, the value is that is equal to 1. But here, the lower Riemann integral means what is that here? Small mi, that is in supremum. First we can take infimum of all this function. Infimum means it is 0, 0, 0 will be there. Then again, if you take a supremum also, you get 0. Is it correct? You get a 0. This is 1 and this is 0. Then we say that the left hand lower Riemann integral is not equal to the upper Riemann integral. Then we say that it is not a Riemann integrable on closed interval a comma b. This is shortcomings. We can make it into a Lebesgue integral. In the Lebesgue integral definition, we need some of the prerequisite. You already know that some of the things related to the simple function. You already know that in a measurable function, we discussed about the simple function. What is simple function? A function is said to be simple if the range of the function is finite. If the range of the function is finite means you already know that is the examples for characteristic function, high function. Then a real valued function, we say that phi is said to be a simple. If it is also measurable, then we can make it into a finite number of values. If phi is a simple, then we can make alpha 1, alpha 2, alpha n can be written in the form of summation that can be expressed in the phi of x is equal to summation I running from 1 to n, ni some chi I or ni into some k of alpha. Then definitely that is in a set of all measurable. You know that product, sum, product, difference and quotient of two simple functions are also simple and also measurable. We discussed in the previous chapter. Now here we consider a step function psi on a closed interval a comma b. Means here psi x is equal to ci for all Xi of I minus 1 is less than or equal to x less than or equal to xi I, where A is equal to, this is a partition, it is made into a subdivision, that is xi naught less than xi 1 less than etc. xi n is equal to B is a subdivision of the interval A comma B. Here we will mean that capital Mi is equal to small mi with respect to this step function Ci for all I running from 1 to n. Because infimum and supremum value of this is same, therefore the Riemann integrable of integral upon A to B psi x dx can be represented as summation of I running from 1 to n, then xi I minus 1 into this Ci, because it is, we can make it into a simple function, that's why. Then R of integral per, this is upper Riemann integrable is equal to infimum of psi is greater than or equal to f integral upon A to B psi x dx. Similar way, lower Riemann integrable R of integral upon A to B f of x dx is equal to supremum of, here we make one more function, that is phi x, it is less than or equal to f integral upon A to B phi x dx. Here, this phi and psi are the respectively step function related to f, whatever the function is defined, where here this we can represent, then if you take infimum and supremum are respectively taken over all the step function. Here infimum is there, if you make a supremum, here supremum will be there, we can make a infimum for infimum and supremum, definitely it become equal. Then the Riemann integral changes to Lebesgue integral function. Now we will discuss about the Lebesgue integral of a bounded function over a finite measure. Let E be a set of finite measure. You know that finite measure. Then the characteristic function of E is denoted by chi E, is defined by chi E of x is equal to set of all x belongs to E if it become 1. If x does not belongs to E, be represented as 0. This is the definition of a characteristic function on E. After the characteristic function, we discussed about the simple function. I already mentioned the definition of a simple function. Again, here a simple function is a finite linear combination of characteristic function. A simple function is a finite linear combination of characteristic function that can be represented here. Phi x is equal to summation I running from 1 to n Ci and chi E of x. X belongs to E. This representation phi is not to be unique. You must remember, if Ci's are non-zero and also it is distinct and EI's are also disjoint, then the representation is said to be canonical representation. This representation, wherever we see, we say that it is a canonical representation. Here we define chi is equal to, you already know, every characteristic function is a measurable function, then this can be written as measure of E. Then integral upon phi is equal to, because you know that we already proved some of the theorems related to measurable set as well as measurable function. Then if the summation become countable additivity property, we can make it is summation I running from 1 to n Ci into MEI. And integral upon phi E can be represented as integral upon phi into IE. If it is written also, we must aware that this is the representation. If phi is equal to summation Ci into chi E is a canonical representation, it is often convenient to represent are phi, which are not canonical. We must remember this. Now we move on to theorems. Let phi is equal to summation I running from 1 to n ai into chi ei, with ei intersection ej is equal to mt for I not equal to j. Suppose each ei is a measurable set of finite measure. Then integral upon phi is equal to summation I running from 1 to n ai into measure of e. Here there is a one simple function, it is a canonical representation is given, and each measurable set ei is, what is that, intersection must be disjoint, and also if each ei is where whatever the ei's are you chosen, that must be a measurable set of finite measure. If these are the properties holds, then the integral representation of phi must be equal to summation I running from 1 to n ai into mei. This, how to prove this? First, we can choose some set. You know that each set can be in the measurable set. We can make that as a union. Suppose there is union u1, e1, e2, e3, etc. will be there. Then if you take a union of all the sets, then it is, because given set itself a measurable set, then if you take a measure, that is union become a summation. These things you already aware, and also we proved the countable additivity of M. Here, let us start the proof. The set AA is equal to set of all x such that here phi of x is represented as A. Means it is the union of all the ei's. Ai is equal to A. Hence, if you are applying A into measure of EA, measure of EA is equal to summation AI is equal to AI into measure of EI. By the countable additivity of M, so that summation of MA is equal to measure of AA, it can be extended to AI into measure of EI. This is because this AA become the measure of EI. That is the proof. Straightforward proof, you must remember. Next, this is the one of the important theorems in the finite measure. Let phi and psi are the simple functions. Simple function means each can be represented in a canonical representation, which vanishes outside a set of finite measure. Means inside it becomes a canonical representation, but outside it becomes 0. Then integral upon a phi plus b psi is equal to, we can represent it as a into integral upon psi plus b into integral upon phi, and psi will be there. And if particularly here it is given phi is greater than or equal to psi almost everywhere. If it is almost everywhere means except in that measure it is 0. That is the meaning you already know. Then integral upon phi greater than or equal to integral upon psi. Means here first there are two functions, phi and psi are the simple functions are given in a finite measure. Then you can take a and b with respect to integration, then that can be written as separately. That is the property of the simple function. In this, we are chosen first, let AI and BI be the sets which occur in the canonical representation of phi and psi. First, we can make a representation. That's why we are choosing AI and BI are the two sets. In that particularly, if you take I is equal to 0 and BI is equal to zeros, then that become A0 and B0. This A0 and B0 be the two sets where phi and psi are 0 because it is given that it is phi is greater than or equal to psi almost everywhere. Then the set Ek obtained by taking all the intersection of this means intersection of Ai intersection Bj is equal to 0. Intersection of Ai intersection Bi and form a finest disjoint collection of measurable set. These are the representation. Whatever the given set, we can make a representation, then that can be written in the form of phi is equal to summation Ak into Ek, k running from 1 to n. Psi is equal to represented as k running from 1 to n, Bk into Ek. Hence, here a phi plus b psi is equal to, we can make it into, because it is running from k running from 1 to n, then we will make it use as a into ak, b into bk are the real numbers into ek as a common factor. If you apply directly, then this become integral upon a phi plus b psi is equal to a into integral upon phi plus b into integral upon psi. Here only to prove the second part, we observe that integral upon phi minus integral upon psi is equal to integral upon phi minus psi, because you must prove that it is in the almost everywhere condition here. If phi is greater than or equal to psi almost everywhere, then integral upon phi is greater than or equal to integral upon psi means we can take it into left hand side, then that becomes integral upon phi minus psi is greater than or equal to 0. Here, the integral of a simple function is greater than or equal to 0 almost everywhere by the definition of the integral. Let f is a bounded function over a set E of finite measure. Analogous to Riemann integral, we now ask the question, when we can expect infimum of integral upon psi x dx and supremum of integral upon phi x dx to exist and to become equal if and only if you must remember psi and phi are simple function. Then the proof is finished. If these two are simple function, definitely this condition is also good. Is it any doubt? That is the fundamental theorem in this finite measure. Now we will move on to one more theorem related to simple function. Let f be defined and bounded on a measurable set E of finite measure in order that infimum of integral upon of psi x dx is equal to supremum of integral upon phi x dx. And depending on, you can see that phi is greater than or equal to f and psi is greater than or equal to f and phi is less than or equal to f. If these two are equal for all simple function phi and psi, it is necessary and sufficient that f must be measurable. Here, what is the theorem states? F is defined and bounded on a measurable set E of finite measure in order that infimum of integral upon psi x dx, that must be here psi is greater than or equal to f and phi is less than or equal to f with respect to supremum, here with respect to infimum. If these in the order phi and psi are simple function, then only if necessary and condition means f is also measurable. If this we can prove in the, we can start with starting with the set measurable set concept. Using that measurable, you know that measurable set can be make it into a measurable function that each measurable function, if it is greater, lesser, and equality, then that function become a measurable function. Here we can start with this. Let f be a measurable. Let mu be a bounded of f. We define ek. Ek is a set. You know that there is a greater and lesser will be there in the measurable sets. Here, and also it is bounded means you know that when a function f is said to be bounded, then there exists some real number m. Mod f is less than or greater than m, we will write. That is the boundedness properties you are studying. Here we use similar way. Ek is equal to set we taken as x belongs to E, k into mu divided by n greater than or equal to f of x greater than k minus 1 mu by n. Because we are chosen here minus n is less than or equal to k, less than or equal to n. Here, since f is measurable, this can be splitted into a intersection of two measurable sets. That's why here Ek can be represented as set of all x belongs to E, k mu by n greater than or equal to f of x, intersection of set of all x belongs to E such that f of x is greater than k minus 1 into mu by n. Because you know that intersection of two measurable set is again measurable, intersection of two measurable function is also measurable, and also you know that EKs are disjoint. Here EKs are disjoint. Also we can represent whole E can be represented as union of Ek. What is Ek? Here k running from minus n to n, that is k running from minus n to n. If you are applying a countable additivity of m here, then what happens here? This become measure of E. This union become a summation k running from minus n to n into measure of Ek. Here we define psi nx is equal to mu by n. Here mu by n is summation k running from minus n and k times chi x of chi ek of x, and phi n x is equal to here mu by n summation k running from minus n to n k minus 1 into chi ek of x. You know that it is given phi n and psi n are the simple function. It can be represented in a canonical representation. After the canonical representation, we can make it into supremum and infimum of the function. You know that supremum and infimum of all the functions are measurable function. We already supremum and so infimums are the measurable function we discussed in the previous classes. Is it correct? Using that concept here, this function must be lying between phi n x into psi x. Then if you applying here infimum of psi is greater than or equal to f integral upon e psi x dx is less than or equal to integral upon psi n x dx, then with respect to e, that is mu n by summation k chi e of x, means it is a measurable characteristic function. This can be represented as measure of Ek. Similar way, if you take supremum, phi is less than or equal to f integral upon e, phi n x become phi x is greater than or equal to integral upon e, phi n x dx. This must be equal to mu by n summation k running from minus 1 to n k minus n into this is also measure of Ek. Hence, if you're observing these two combined with this, we can make it into 0 less than or equal to infimum of this minus this less than or equal to mu by n into, because k minus 1 is less than the k, then this become k running from minus 1 to n measure of ek, then measure of ek by using 1, because measure all the sum of ek can be written as measure of e, then this become mu by n into measure of e. 0 less than or equal to mu by n into measure of e. Since n is an arbitrary, if you make it tends to n, then this whole thing become a 0. If this is 0 means 0 less than or equal to less than or this function less than or equal to 0 means this is equal to 0. This is equal to 0 means this is equal to my a minus b is equal to 0 means a is equal to b, means you get infimum of psi is greater than or equal to f integral upon e psi x dx is equal to supremum of integral upon phi x dx, phi is less than or equal to f. Next, the converse part. What is the converse here? This we can take, we can prove that f is measurable. Here, this is equal means for every n, there exists a phi x, psi x and phi x will be there, means we can take phi n and psi n are the simple function that must be lying between the f of x, because here greater and lesser symbol will be there, then definitely it is lies between the f. F is lies between phi n and psi n x. Then the minus, definitely it is less than or equal to any integer 1 by n. We can make psi n means infimum of all psi n is psi star. In supremum of phi n is phi star. You already aware phi n and psi n are measurable function, because we proved in the measurable function all supremum of fn's. Fn's are series will be there, then definitely supremum of fn's are all measurable function. Definitely this is measurable means the left hand side is also measurable. Then we can make here phi star x is less than or equal to f of x less than or equal to psi star x. We can make it into a delta, that is one set of all x belongs to E, such that phi star x is less than psi star x. Then we can take a union, you get the element here. If you take the measure of this, the whole thing, it is a finite singleton set. Singleton set is 0. Measure of delta is 0, means since phi star is less than or equal to psi star, and measure of that set becomes 0, but we conclude that this is equality when if it is almost everywhere. But phi star is less than or equal to f means definitely here f is equal to phi star almost everywhere. Means this means that f is measurable. Is it any doubt?
Yes.
Please read 1 or 2 times. I think I already sent a